The homing procedure just finished, and now I should be able to do this. I'm honestly surprised that I haven't managed to break this arm permanently by crashing it so often. But since I haven't, I might as well start the video series about restoring this arm. A couple years ago I was actually going to design and build my own arm, but then I found this one's surplus for actually less than it would cost to get the components. Now, even though there isn't necessarily that much mechanical work to be done, there's still a lot that goes into making this arm work. This isn't an easy project to document. You're always jumping around to different topics, and you can only learn something for the first time once, which may change the direction of the whole approach. But when I go searching for this stuff, the most I'll see is a video of an arm moving around and that's it, which isn't that great of a learning resource, so I figured I would at least try. Now, you might not learn anything anyway, but I suppose that's beside the point. Now, I'm not going to be able to cover everything in this video, so I'll just stick to these topics, and it'll just be sort of an introduction. Solid aluminum. It's about 3.5 feet tall and weighs 70 pounds. Let's get it to the other room where I can take a better look at it. Something like this I think I'd describe as sort of a couple levels up from those cheap servo or stepper motor arms you can find, or those grandmother with osteoporosis arms that the machine learning guys are always working with. Compared with this wooden arm that I made previously, it is incredibly rigid. More like a, proper machine tool. It's also quite a bit stronger than those cheap servo arms. It's meant to hold something, a couple pounds at arm's length, much like your natural arm. And as best I can tell, that's about what this was designed to work on. So the company CRS Robotics is no longer around, but I think Thermo Scientific bought them, and they sold arms for a while that would pick up and move laboratory test samples in and out of holders and things like that. The sort of mindless, repetitive tasks you would trust a robotic arm to do. Which also brings up the point that an arm of this size and this weight can injure you, unlike those tiny servo arms. So while it might not be able to throw you across the factory floor, it could probably break your wrist or cave in your skull on a good day. As for this arm specifically, you ever see those technical college commercials on TV that are come to insert technical school, you get to play with the robotic arms? Well, that's where this came from. I'm 99% sure that the only hard work this arm had to do in its life was deal with being abused by students in the basement of some university. Hence the NASA logo on the side, probably put there by some overzealous grad student and not having really anything to do with NASA. As for why I have it, it's because this is a pretty old arm. It probably got replaced at some point by a new arm from some grant or something. It was built all the way back in May 2001. And as we all know, electronics have gotten a lot more smaller and more integrated over the years. And so it is with this arm. In current day, I think probably the whole arm would be self-contained and, something arm-sized. But as for this, it also comes with an equally heavy 70-pound box of electronics. There's a secret hidden panel with fuses and circuit breakers in it, and an emergency stop. It actually doesn't make a bad seat as we inspect the rest of the arm. It is a 6-axis design, 1, 2, then this rotates, 3. The elbow and shoulder are locked, and then the whole thing spins around like that. There's definitely some expensive feeling gearboxes in there. I really don't know what this thing would have cost new. Now, probably the first thing you'll notice is these massive shoulder pads that no modern arm seems to have. So let's take a look at that. And inside is a quite substantial brushed motor. There's the brushes right here, so this will be DC. A big industrial encoder on the back there. And the connectors for those things underneath. That's pretty fancy. The other side has more or less the same thing, except for another pair of wires. Actually, a couple other pairs. One is for the index sensor. We'll see some more of those in a minute. And this one also has a brake somewhere on it. So one of these motors is for the elbow, I guess you'd call it. That's driven with a belt. And the other one is for the shoulder, the whole thing up, down. And since I have the camera out, I've never actually looked at the gearboxes. Actually, only the other side wanted to come off. Let's see. Oh. Well, there goes that. There's the belt. We got a Sumtech optocoder with a model number that does not appear in Google. It's probably too small quantity, too long ago to have the data sheet still out there. A and B and A0, B0, and Z, which I think is an index. And the motor, Cleveland Motion Controls. I'm sure this also does not appear in Google. And then up at the top, a little brake. You can actually see the friction material in there, and then that's a magnet. Pull that plate up. Actually, that's pretty similar to how the brakes in electric wheelchairs work. And then at the top, we got this little slidey thing, just so if this axis and that axis aren't perfectly aligned. It's also pretty common, I think. It's a better look on the inside of, well, various things. Connectors, and that little hose right there, little tube, is because this has an air input, which comes out, well, not this, but there's another port on the other side for air. Here's a better look at that belt. So I move the elbow up and down, but what it reveals is that the gearbox for this, there's no gearbox down here at all. It's actually in here. And from what I can feel, there's no noticeable backlash at all, which is exactly what you want. Take a look at this little guide plate thing here, which I guess is to stop these wires from curling around the wrong way. Look, that's obviously a hand countersunk screw hole there in some little plastic piece that looks like it was also carved out and sanded by hand. Gotta love all those hand-built parts and these low quantity like thingies here. You know what else I've just realized? As this moves up and down, that belt rotates, which I guess in theory would make the elbow motion dependent on the shoulder motion. I thought this was all independent motors for each axis, which I guess is technically true because it's only like a half rev of this motor does anything, so it's probably not going to matter that much. You know, I better put this thing back together before I break something. Oh, hey, that's something I didn't notice. Where they milled away the inside, I guess to reduce weight. I thought this thing was all made out of flat stock. Well, I guess that's not true. This part here was clearly either cast or welded. Probably welded. On the same label as on this side, I guess it wants 15 inch-pounds. Well, then that's what you're gonna get. It's 15. Doesn't seem that tight, really. And now we can take a look at the top section, starting with that right there is the air outlet, or maybe it's vacuum, I'm not sure. I've never quite seen a connector like that. But I think both of these holes is where the air comes out of. Should be able to lift that up. There we go. And one on the other side. This is an electronic connector. I think this would have originally come with a stereotypical robot arm claw thing, which I did not get. But there's the inside. We got more belts and gearboxes. And for the ones on the wrist, that is a much smaller brushed motor in there with more brush covers. And I think that there on the side is another rotary encoder. We got some circuit boards And here's where the all the cables are curled up so they can move around. Right in here, the motor for the wrist, the rotation of the wrist is actually in there. Now right here, that's one of those zero sensors I was talking about. It's actually, I think when it comes to the start of that gap right there, right like that, that's where the zero position is detected. So when you start up this thing, the encoders are incremental, so you have to drive it until it hits the end stop, and then you kind of know where the position is. This belt is still in excellent condition. And again, I really can't detect any backlash at all in that gearbox. Over here is the index location for the, I guess, forearm rotation. It's another one of those, I guess it's a Hall or inductive sensor of some kind. Non-contact. And besides noticing that it's made in Canada, the last thing we have left on the arm itself is the inputs. We have that air input and then the two big connectors, which actually are just breakouts for all the encoders on that the fine pitch one, and connections to the motors and brakes and stuff on the bigger connector. Now this didn't come with the cables, so I had to make my own. Surprisingly expensive, these connectors, but at least they're not as bad as some that I've come across. And I couldn't find cables that had, you know, a million wires inside, so these are just a bunch of serial cables, and tried to divide them up per encoder, so each axis gets one cable. Luckily, the pinout for these is in a manual I could find. Next up is the electronics, which is really where the story starts as far as making this thing move. And you'll note the disheveled interior, but this is kind of how the original configuration of it was. This here is the original main board. And so from the two connectors on the back, on the other side, the power connectors go down to some power stuff over here. The other connector goes onto this board, which originally this ribbon cable plugged in right over here. And this board here is what did all of the controls. As best I've been able to figure out, these programmable logic chips and RAM and stuff. Here's a DSP chip of some kind here. This stuff here did all of the low-level control loop stuff. So your PID controllers, counting and keeping track of the encoders, stuff like that was all done in here. Maybe motion planning as well. And then the application and the stuff you actually wrote was on this little 486 industrial computer over here. And this whole thing has not just the robot arm, but also a whole bunch of IOs that you could have. So there's a connector here, a whole bunch of IO pins, various serial ports. It actually had this fancy expansion port with even more IOs on it. It's not like it is now where you can just stick an Arduino on something and have as many IOs as you need. Now, I spent a good deal of time scouring for the original operating manual for this thing here, and I was able to find some things, but not everything. This thing here actually had a pretty substantial serial interface, so you could just connect a serial terminal up to this. You get a little prompt, you can enter in programs, edit files, and all that's stored on this computer here. But the manuals I found, they don't have the original software that would have gone with this. This had a PC app of some kind also. And they don't go into the bringing up of the machine, so how you set the different PID loops. And worst of all, this is in the era sort of before flash memory. So all of the data is stored on SRAMs, which are backed up by this battery right here, which is actually still good. But my problems really started one day when I was taking a look at this thing. You know something I should do? I should back up the BIOS chip on here. So let's pop that out. Alright, what's the part number we got on this? Uh-oh. And just like that, I accidentally disconnected that SRAM from the power supply, and all of its contents were gone forever. So, I could either spend a really, really long time reverse engineering this whole board, or we can take it out and replace it with something else. With the controller board gone, it's probably a good idea to review what we actually have left in this case. So under this shelf is actually a big toroidal transformer and some capacitors. That's the main power supply. These motors run at something like 70 volts, and the small motors up in the wrist are, I think, like 24 volts or 30 volts or something. So the power supply is all under here. Over here, we have the actual motor controllers themselves. These three here are off the shelf, although I can't find data sheets for them. They are off the shelf controllers for the big motors, 1, 2, and 3. And then this one over here is a custom motor controller design for the 3 smaller motors up there. Now I say motor controllers, but these are more like motor amplifiers. They're all analog. So to drive the motor, you drive them with a minus 10 volt to 10 volt signal. I have my 0 to 10 volt voltage generator here, so do that. So it's 0 volts, it's stopped, and then as you go up and up to 10 volts, it goes in one direction from 0 to full speed. And if you want to go the other direction, you go 0 to minus 10 volts. And that's true for all 6 of the channels on here. They all use the same signaling. Meanwhile, on this, I guess you'd call it the power and I/O board, you have several large relays which connect the power supply to the motor controllers. They're not connected all the time. When you enable it or push the emergency stop, these turn on and off to physically disconnect power from the system. Also on this board, we have various things, a whole chain of optocouplers. Those are for those digital IOs I was talking about. That actually comes in over here. And then these missing sockets were, I think, NPN arrays for, transistor output. You get a few relays for relay outputs. Over here, I think this is logic for doing fault detection. The original software is able to detect when these fuses or circuit breakers are blown, so it can stop automatically somehow. So then it was just a matter of tracing out different things I was interested in and bringing them up to my own connectors for my own control board that I was going to make. And the original board has all these standoffs here to mount the other board on top of it. So I got a nice piece of acrylic to go on there. That will go something like this. And I'm using acrylic mainly because I can just take my marker and see through it and mark exactly where the holes are supposed to go. And the whole reason I had this controller off today is that I forgot some pull-up resistors. So we gotta have pull-up resistors here for the homing switches. And then since they're RS485-like, we gotta have terminating resistors. These are the ones I forgot. And there was really nowhere to put them, but luckily where they need to go is right across the top and bottom pins here. So that was certainly lucky. Hopefully these little SMD resistors don't bust on me. And introducing another several day long continuity error, here are the electronics as they're currently installed in the box. Let's get a closer look at our main board here. So this is now our main control board. The inputs from the encoders on the arm come in on this cable, and these are differential RS485 or RS422 level signals. So we have to change these into TTL level signals, so I have several receiver ICs here, 4 channels each, so the 5 of them give us 20 to cover the 18 channels that come in here. And then for the encoders, I decided to go with dedicated quadrature encoder counter ICs. So you could do counting the encoders in ISRs in firmware here. Some microcontrollers, probably even the teensy this has, can just count encoders like that's something built into their function. Like they have I/O blocks that'll just do that for you. But in my case, I went with external ICs. These can count up to 32 bits of count, which is plenty, thousands of rotations per axis. So after these 6 counter chips, the encoder values are now digital. They go into the microcontroller. And then for our output, our motor drives take -10 to 10 volts DC signals. So I have 3 2-channel DACs here and a little reference chip to provide our 10-volt reference. And these take care of converting a digital signal into an analog one to drive our motors. Now there's other stuff on here like opto-isolators to detect faults on the motor drives that actually have a fault output. I've never actually seen those turn on, but they're there. And then a few things like being able to turn the main power relays on and being able to detect when the e-stop is pressed. That's this stuff here. There's really not a lot on this board. The main star of our show is this teensy 4.1 right here. Although I'll be honest, if I was starting this from scratch today, I'd probably go with an STM32. I've been doing a lot of low-level stuff with those recently. The main advantage of our teensy is that it's really fast. So this is a 600 megahertz chip. That's a lot of instructions you can get in not a lot of time. Unfortunately, what you don't get is any kind of low-level debugging stuff, which makes it a little bit harder, but it's fast enough it can do printf debugging pretty good. Now the other feature I was really interested in with the teensy is that you can install extra RAM chips on the bottom. So this is actually 8 megabytes and then another 8 megabytes of external PS RAM on here, as they call it. This is RAM that runs on SPI, and it's obviously not as fast as the RAM that's built into here, and even at that, this still has like a few megabytes of RAM, which is a lot. But what I intend to use this RAM for is sort of a record and play mode for the ARM. So as I'm running the main control loop, I can just record values directly to this and then play them right back. Kind of like a WAV file for audio, except this will be playing back the PID set points. And there's also a built-in SD card socket, so I can just stick a 16 gigabyte SD card in there and have basically infinite room, whether that's for playing back samples or storing configuration data or whatever. A very powerful chip this teensy is. The teensy also comes with plenty of options to actually get those samples in and out of the thing. So I could use the very well supported USB device, or I could use the built-in Ethernet. This is 100 meg Ethernet on here. You can also spot a mistake I made when I hooked up the index signals. So these counter ICs want the index signal inverted from how I had it wired before. But since these are just differential signals, I can go and cut the cable and then physically swap those 2 pins so that now they're the correct polarity. But we'll talk more about the index signal whenever I talk about how I home the whole ARM, which will probably be a different video. Now the most important job of this control board is to run the main control loop, where periodically, several times a second, I have to read in the data from all of these encoders, do whatever PID or other control methods I'm going to do in the software, and then write out the result to the DACs. And this runs on a timer interrupt. I'm not sure what frequency the original ARM would have run at, but I picked 1000 hertz for this control board just because it seemed like a good round number and in line with what I could find. And if I hook up a scope, we can actually see that 1000 hertz interrupt running there. So I just have it toggling a pin when it enters the ISR and when it exits the ISR. So it's a pretty even 1000 hertz, very low jitter on this. One thing to note, it spends 72 microseconds inside the ISR, but most of this 72 microseconds is being used to transfer things in and out of those counters and the DACs. So I'm constantly reading all 6 chips for the counters and then writing 6 different values of DAC to the DACs, and that's all on SPI. So most of this is just SPI transfer time, and those chips are running pretty close to their limits in the data sheet. I think the counters can go up to 5 megahertz and the DACs are more like 10 megahertz. These are both running pretty close to what they're spec'd at. Now, I should be able to use DMA transfers, and then it will turn this SPI transfer into something that runs in the background, so I'd actually get back most of this time. I haven't really figured out how that works yet. Haven't done a lot with DMA in my time, but I mean, even as is, 7-8% CPU time does not seem, like it'd be that big of a deal. You should be able to get a lot done in the rest of the time here, so I might just leave it. Alright, well here we are in the robot arm test area, also known as the furnace room. So I got the electronics hooked up, USB, couple serial ports going over to my laptop. I can plug in this, and then we get 2 serial ports. One here is like a command interface. I can type stuff in there and like change the PID gains. And then this one is sort of like a live view. So if I just go and turn this, one of these is the encoder value. You can see that value changing. Alright, I don't remember all the different commands. I think to home it, it's Z. Let's see. Oh no, it's not. First I have to turn the main power on. Okay, that should have turned it on. It also should have turned off the brakes, so this now is loose. It is heavy. You wouldn't want to get bashed in the head with that thing. Okay, now I can push C. That should be the homing sequence. There we go. It has started to turn the wrist. And now that it's home, the PID controllers are all running, so they are trying to keep each joint at the position that it's currently in. So whereas I could turn this previously with my hands, now I can't. And it is, even though the brakes are off, it is still trying very hard to keep it in position. If I do turn it with my hand, you can just see those values. See, it's just trying to push back slowly back to 0. Now, here's where it gets sketchy. So, where I left off this project, I got the PID controllers. I did not do any kind of motion smoothing. I think I had just barely started on something that would sort of let me move the axis smoothly, or just at a very low rate of speed. That's not it. There we go. So you can move it slowly. But if I turn that off, now each step it's commanding the PID controller to go there instantly. So it moves as fast as it can to get there. And that's where things get a little scary. Let's try this one. If I go back to moving it slowly, oh, I guess it moved back to the original position. But that's moving slowly. So this is again just a very slow speed, no acceleration, no jerk control. I mean, it kind of works, but clearly the next thing here is to make some kind of control that is not just me pushing different keys. I do have plans to make like a little arm that you can position and it will move the big arm. But in the meantime, I can use something that's been in my junk box for a while. One of these. This is a controller for like a crane or a backhoe or something like that. Except it's not the real one. This is for training. So inside of here is mostly empty. And it just so happens to have 6 of these control levers, which are these things. I'm not actually sure if these are the real ones used. They seem like the real ones would be Hall effect. These are basically just a spring-loaded potentiometer, but they're more than good enough for what I need them for. And so here's another one that I've prepared earlier. So we have our same 6 levers as on the original. And then up here what I've done is remove all the existing components and then make a nice 3D printed bezel to go over the top of it. So behind here it's a Swiss cheese mess of holes, all nicely covered up by this 3D printed piece here. So up here we've got a nice Hall effect joystick that I also happen to have. And this is a rotary switch. I plan to use this as like the mode select, so it'll be like, this is direct drive, and then you home it here, and then go into PID mode, and then inverse kinematics, or whatever else modes I come up with. This one here is a potentiometer. This is probably going to be like the master speed control, so it'll be, you know, slow is down here, and then if you want faster, put it all the way up. The emergency stop wired directly into the other emergency stop on the control box, and then just some switches and buttons and stuff, and a little encoder wheel to round out what I could fit on here. Oh, and an LCD panel. On the side here, a little circular connector to go over to the control box, and programmable with USB, so I can do updates and stuff. And we can take a look inside. Normally I'd use something like a blue pill or a black pill board in here, but in keeping with the teensy theme, I found a teensy 3.2, which are not actually made anymore. But the reason I went with this is because it has a whole bunch of ADC pins. I actually need 11 to control all the different ADC things that are on here. Also, this is all wire wrapped because I found that to be a lot cleaner than just soldering everything if you're going to be poking around in here and changing things, which is bound to happen at some point. This Hall effect joystick here is really the only odd thing, is that it runs on 5 volts, so I needed a 5-volt regulator here. I actually didn't need a heatsink nearly this big because the whole thing draws almost no current. And from our 8-pin connector on the side here, we have 2 pins for the emergency stop, 2 pins for power, and that leaves us 2 more pairs, which is perfect for some kind of differential signal for UART. And RS422 is an obvious choice because it's full duplex. And it turns out you can just buy a cheap, ready-to-go Amazon special board for RS422 and hopefully be done with it. We'll see how this works in a minute. Finally, just going along here, you can see all the rough cutouts of where some of the original holes were, and where I went along with a Dremel and cut out the openings for all these controls. But the bezel cleans everything up very nicely. So now this is powered on, and I've already went through the teensy on this to do dead zones. So for instance, there is a dead zone here, but when I move it off center, going down into here, it goes from 0 to +1, and then in the other direction, -0 to -1. This operator console has also come a long way since whenever I last cut in the video. So now we have a whole bunch of indicators of different things that will happen. So like the homing indicators, so when it's hit those proximity home sensors. So there's one, and then underneath that we have the counter value, just the raw counter value. I haven't actually figured out, how the counter values correspond to actual angle positions on the joints, but we'll get there. And then this is a new feature I just added, where it will beep and turn yellow when it's pretty much at the limit of the joint travel. I can also do things like turn on and off the PIDs. So that's PIDs off, PIDs on. Then we have the mode selector. So this is like direct mode. You turn on and off the brakes, turn main power on and off, emergency stop. Plenty of good things on here and plenty of room to add more things. And then down here at the bottom, these are the actual raw data that I'm sending over the serial port to and from this operator console box. So that's just for debugging. Now I will say you can actually update the whole screen at the 100 Hertz that this runs at. Now I could try to use a frame buffer and then just constantly update the screen using DMA in the background. But the Teensy 3.2 actually doesn't have enough memory to render this whole screen. And that gives us that whenever we draw something, it just takes however long it's going to take to draw it, which for a line or something is only, might take 1 millisecond to draw this whole line. So with this operator console, I get 8 milliseconds after the serial transfers are done to just draw whatever I need on the screen. So that's pretty much what I do. There's 4 or 5 different sections that draw different things in the time that I have. Now I've done it, I've broken one of the gearboxes. So this is the very last joint, the, wrist turn there. And it gives us a good chance to see inside. It is a harmonic gear. So that there is a very fine ring gear. And this thing is the flexible spline that goes with it. So as I push this in, this way it gets bigger, so the 2 teeth on either side there interface with that ring gear. And we got the so-called wave generator here, which is basically an oval-shaped ball bearing with a flexible outer raceway. But what happened to it was that the end stop broke. So the original end stop is this little screw right here, and it goes into this slot like so, and that interfaces with that pin on here. So when this comes around, it pulls on that spring like that, and then the screw head actually goes under an inductive probe, and that is the end stop. So that's how it zeroes it out, and that screw snapped right off. Now what I could do is just replace the screw here and call it a day. But this is the only axis on the arm that I could get away with an infinite rotation, if I can come up with a way to index it without some kind of contact. So what I'm going to do is take one of these little things from your serial port. This is a 440 thread, and it screws right into this bearing. The other side has these screws in it to hold this whole thing together. But after I mill that down and drill this out, I can put a little magnet in there and then fit a Hall effect into this hole. I'm going to have to find a way to mount that though, because I cannot take this off. It is glued on there firmly. I already tried. Alright, I've put the wave generator back in, so this is about to get reassembled. Need some more grease though. And I've drilled 2 mounting holes in here so that I can fit a little 3D printed mount like this in there that'll hold our Hall effect sensor. So let's see if that fits. Yeah, it looks pretty good. If this thing clears the magnetic pin when I put the other piece on there, we'll be in good shape. And the screws. Looks pretty good. But I can access all of this while the rest of the gearbox is put together, so I'll be doing that next. I guess this will be the only time when I can see the wave mechanism operating, so let's see what that looks like. And here's the pin in question. Loctited on there earlier today, and it is a magnet. Now it's time to put the ring gear back on, and the previous couple times I've done this, I found it easier to do when this is already moving. And there we go, it's engaged. And there we go. And it really doesn't sound any different, so that's probably a good indication that everything's lined up how it's supposed to be. And with the back put on, we should see our magnet come by in that window. Yep, there it is. Let's make sure that the little mount thing clears it. Yeah, seems to. And now I can finally test it. We'll use this one with it very messily super glued in there. The real one will be epoxied. And put that in here. And then I can replace this Hall effect here with this one. Oh, that's looking good. We're not having any kind of weird double hits or anything. So I think that's probably going to be it. These Hall effects, by the way, nothing special. This is literally the first thing that comes up on Amazon when you search for a Hall effect. But they're pretty neat. They can supposedly take up to 28 volts. Epoxying is in progress, and I just have a sewing needle holding the Hall effect sensor down into position. You can also see here where I had to carve away part of the housing just to get it to fit when installed in the arm. And I guess I better make sure it still works. Yes, it does. It's also interesting, you can see the hysteresis that this sensor has. So there's a threshold to turn it on, and then you have to pull it away farther to turn it off. I'm not sure if that's the metal causing this, or if that's something intrinsic to the sensor. But of course, nobody really knows how magnets work. Motor is installed again and temporarily wired up here. And now we can see if it actually works. So we can go to the control panel, main power on, and let's see, maybe I can get them both in shot here. We're looking at that homing indicator. Ah, there it is. So that is a success. And infinite rotation. Ooh, it looks like we may overflow the field for what I've picked to show the counter position there. I'll have to fix that. Wires are back together. We just need to make sure that no wires rub on anything that they're not supposed to. And that's looking pretty good. You know, now that this is starting to come back together, it'd be a pretty good idea to grab a square and write down some of the encoder counter positions for some of these angles. And for that, I need to be able to turn the PID controllers off. So right now this is trying to reach its target position, so it's pushing back against the belts. And if I turn the PID off, that's push hold this, bring that down. Now the motor spins freely. Okay, I've tried to center the tilt of the wrist, so that's centered, and then we got this axis, and we got that axis, and combining them, that looks pretty good. Now, same thing true of these two axes. Let's see if I can do this with one hand. Well, those must use different values for encoder. Now we got another problem. It's with this axis and the end stops on it, which are down here. So I actually have to take this whole thing apart. So first I'll try taking off this top piece. There we go. And now I think I have to undo some of these. Well, I don't know. I bet 3 of these remove the cover, and then the other 3 do something else. I don't know. This is a metric size. For some reason, this arm likes to switch between metric and English units quite frequently. I think that is a metric size. And there we go. Under that cover is indeed another harmonic gearbox. Although this doesn't really help us in getting this thing off to get to the end stops. Well, I wasn't expecting to find this in there. Let's see if I can get it out. That is a big snap ring. This is the part that actually needs to be fixed. It's right, well, that spring is not supposed to come out. This screw head, it's not supposed to do that. This one is finally done. I wasn't able to show it on camera. This one was much more difficult. Probably 10 times as hard as that other gearbox I did. Same deal where take a bunch of stuff off, but yet it won't come apart, probably because it's been Loctited in there. Although this one is really bad. I mean, you take this off, that's the top of the gearbox. This whole thing comes off. There's 2 bearings in here, and you still can't get that out. I think you would need to take off the encoder, take out the motor, then undo some screws down there to get the bearings off, and then you could finally get this ring off. So instead, I just very carefully drilled a new hole next to the old one, tapped it, and put a new screw in there, and also a new screw in the side, and that should do it. And since this is open, this is the only time we're going to be able to see some of the stuff. So another board with the connectors on it. And this is what wraps around the wrist to the other end of the wiring harness, which is at the top. And yes, our little air hose is still making its way through the entirety of the arm. So for the last thing, I want to show off the record and play feature that makes use of that PSRAM on the Teensy. So I have it just wired up to the encoder button right now, so that's start and stop recording. So I'll hit start, and then we can do some moves. Move the arm around. And stop. And now I currently have no algorithm to get from this position back to the original position, although we can play it backwards. So this runs at the native 1000 hertz that the PIDs run at. So this is as good as you're gonna get in terms of replicating the original inputs here. And there we go, now it's back to the start. Now I can play it forwards again. This can hold around, a few minutes of motion here. So it's kind of like a wave file, but for movements. And that beep is just another feature that I added just today, which is software limits. So if I drive this far enough, now I can't crash it into itself. Which is nice because, as I said, I already spent yesterday night replacing the end stop in this from crashing it into itself too much. So that should be pretty helpful.